All right, let's take a look at the book here. And so last week we talked about determinants. We talked about how to find determinants of a square matrix. And remember, the matrices must be square matrices in order to have a determinant. We looked at finding determinant using cofactor expansions. And we looked at section 3.3 also, by the way. In section 3.3, we looked at some of the properties of determinants. So real quick, just want to go over those. The first property we saw was that the determinant of AB, the product matrix, is going to be the product of determinants. That was one of the first properties. The other property was the constant multiple. Determinant of a constant multiple of a matrix. You raise the constant to the nth power, where n is the order of the square matrix. So for example, if you have a 3 by 3 matrix, and you multiply, you do 5a, because you have a 3 by 3 matrix, 5a, that would be 5 cubed, determinant of a. And that's that one. The other one we looked at was this important theorem that told us the square matrix is invertible if and only if the determinant is not zero. And the consequence of this theorem was that we were able to enhance our list of statements about what you call it, about the inverse of a matrix. Okay, I'll show you those in a few moments. The equivalent statements that we have about a non-singular matrix. I'll flash that in just a moment. Now, this theorem 8, the determinant of inverse of a matrix is 1 over determinant of A. And again, these theorems are there to help us, so we don't have to, for instance, find the determinant of A inverse directly. We can, once you have determinant of A, just take the reciprocal of that, and that will be the determinant of its inverse without even finding the inverse. So that's the beauty of this theorem. Okay. And here you go. This is the important takeaway from the section. Prior to section 3.3, we had items 1 through 5 already. We had these before this section. And then once we added the determinant to that, we can add one more to our list of equivalent conditions. So if A is invertible, for example, that means determinant of A is not 0. If determinant of A is not 0, that means the matrix is invertible, which in turn, it means the solution to the linear system, it has a unique solution. The AX equals 0, remember this one, has a trivial solution, and we call that the homogeneous system, right? AX equals 0. The solution to homogeneous system is only trivial solution. What that means is this. The only way this can be 0, the system is 0, is if x1 0, x2 0, x3 0, and so on. And this is interesting. If you do a Gauss-Jordan, row equivalent means Gauss-Jordan pretty much. If you do Gauss-Jordan on A, that matrix A is going to look like an identity matrix. I, identity matrix of order n. So there you have that one. Now, property number 5, that's fine, but usually we don't do this part. But again, it's a true statement, but we're not going to use elementary matrices hardly at all in the course. And now this new important thing, determinant of A is not 0. So if you look at the example that's on the screen, example 5, for instance, this system, a 3 by 3 system, linear system, I'm looking at part B, the 3 by 3 system, its determinant is negative 12. So this determinant is not 0. Well, what does that mean? And this is not a homogeneous system, right? To the right, I don't have zeros. So that means item number 2. That means this system has a unique solution. a unique solution. For column matrix B, so that means for x1, for x2, and x3 variables. So that's a good thing. That is a good thing. If you look at this one, the determinant is 0. Now remember, the determinant cannot be 0. If you want to have an invertible matrix, determinant cannot be 0. If the determinant turns out to be 0, such as the case in part A, then in that case, the matrix is not invertible. That means there are dependencies among rows and columns of this matrix. And we identified some of these last time, like for example, I don't know, you can multiply the third column by -2 and look at the second column. You see that? Multiply third column by -2, you get 2, -2, 2. So that's the dependency there. All right. The determinant of a transpose matrix is the same as the determinant of the matrix itself. That's the other property you looked at. And I think that was it. Now, I was going to look at just a few exercises because I don't think we did many of these exercises before. So, does anyone have any particular one that you may have tried either from your homework or just curiosity that you wanted me to look at, or should I just kind of randomly pick a few of these and work through? Anyone? No particular exercise? Okay, so if there's no particular questions about the homework, then let me do this. I'm going to go ahead and for instance, let's take a look at number 10 here. Okay, exercise number 10. I think last week we may have looked at one of the numbers from here. I believe we did that. So let's take a look at number 10 tonight. Start with that. And in exercise number 10, I'm going to write it on my notepad here. So this is section 3.3. And again, I'll share it with you, my notepad, what I'm writing on. I'm just pretty much writing problem exercise number 10 here. In exercise number 10, matrix A is made up of 4, 16, 0. The second row, 12, -8, 8. The third row is 16, 20, and 4. Okay, so I have that one. The question reads, use the fact that the determinant of a constant multiple of A, I'm writing that as well. The determinant of a constant multiple of A is C to the n times determinant of A to evaluate the determinant. Okay, so now let me switch to my notepad so you can see what I'm doing here. All right, so this is what I have. I've copied number 10. Here's matrix A, and we want to verify this. We want to find the determinant of A using this way. So I'm not going to go to Symbol Lab, for example, or the other matrix program to find this determinant. Let's do it the way they're asking us to do it. So what do I need to do? Well, if you look at this matrix, what do you think we multiply this matrix A? Looks like they multiplied matrix A by some number. What do you think the number is multiplied by? Look at what the GCF, in other words, is for every number in this section. 4. Very good. Very good. So 4 is the numbers. So in other words, now if you want, here's how we get 4 cubed. Of course, we know the answer. The theorem said is C to the n, but let me show you why that is the case. I could factor a 4 from the first row. When I factor from the 4 from the first row, so that's like 4 times 1, 4, 0, and then 12, -8, 8, 16, 24. And then I can factor another 4 from the second row. So I have 4 times 4, times 1, 4, 0. Factor of 4 out of 12, we get 3, negative 2, 2. And then in the third row, let me repeat the third row. Again, you don't need to do the way I'm doing. I just want to show you where that c to the n comes from. And then in the third row, I can factor a 4 from the third row. And now this is the whole matrix, 1, 4, 0, 3, negative 2, 2, and then 16, 24. So you can see now I have 4 times 4 times 4. So that would be 4 cubed times the matrix 1, 4, 0, 3, negative 2, 2, and 16, 20, and 4. There you go. So that's what that is, right? Now, so the determinant, therefore, the determinant of matrix A, and A is the original matrix. The determinant of this matrix is going to be 4 cubed times determinant of the factored version, 1, 4, 0, 3, negative 2, 2, 16, 24. Perfect. So that's the determinant. Now, at this point, you could just, what you call it, you can do it by hand, or if it's okay, let's go to our program, and I'm just going to input this into to the website. So let me change my share here, stop share, and then change it to, I'm going to, I believe it's in this one, share. Yes. Oh, the last one. Thank you. Let me see. Thank you for, I have a message in the chat. I was able to catch that. This is absolutely correct. I don't have that right. So this row is not accurate. I
You just forgot to factor the 4 out of the third row.
Yes, sir. You got it. So if I did say do it, and I just copied it again. So that's going to be 4. This will be 5, and this would be 1. Thank you for that. Yeah. So I do need to clean this. Let me clear it. Hold on. Give me one moment, please. Okay. There. I'm going to do this way, so it looks better. So it's going to be 4, 5, 1. I'm going to use my whiteout rather than scratching or scraping it. There you have it. So the number turned out to be 4, 5, and the last one becomes a 1. A 1, so that's 4.
Does it become a negative 1?
Not negative 1, because it's a 4. See, in that spot, I have a 4. We were factoring a 4 out of 16, 20, and 4. Right? This one is a 1.
I think in the book it was a negative 4, unless I'm looking at the wrong problem.
No problem. Let me switch to the book. Thanks for pointing that out. Let me just, it never hurts, because I'm sure I make mistakes. Number 10. Thank you. Absolutely. That is a negative 4. Negative 4. Thank you for catching that. Thank you. Thank you. Thank you.
Yeah, sure.
All right. Fantastic. Again, thank you for that. All right. And that would be 4, 5, negative 1. Looks good now. Again, thank you for catching that. All right. Now I'm going to go and change my share. We're going to go and look at the program that does this. Let's see. There you go. Matrix calculator. So I'm going to input the matrix 1, 4, 0. And 1, 4, 0 tab. 3, negative 2, 2, 3, negative 2, 2, and we have 4, 5, 1. 4, 5, 1. and determinant. So it looks like the determinant is 8, correct? The determinant is 8. And again, please verify, make sure I transpose all the numbers, caught them. It looks good. So this is going to be 4 cubed. Now, 4 cubed, what is 4 cubed? 4 times 4, 16 times 4, 64, right? 64 times the determinant turns out to be 8. So whatever that product ends up being, right? And that's what that is. 64 times 8. So that's 60 times 8, 480, 400, 480 plus 8 by 4, 32. So it looks like 512 if I didn't make a mistake. Now, we can verify this, by the way, just to make sure we got it right. I'm going to go ahead and put the original matrix now in here without manipulating it. So it's going to be 4, 16, and then this was 0. The next row was 12, negative 8, 8. The last row was 16, 20, and negative 4. And there it goes, determinant. Ooh, 2,304. So something, we didn't do something right. What did we not do right? Make sure I got 1, 4, 0, 3, negative 2, 2, 4, 5, negative 1. And this should be 4 cubed, right? So did I do something wrong, folks? Can you?
I can't tell. I found the determinant of the factored matrix by adding 2 rows, adding the first 2 rows to the end and doing that multiplication trick, that
Okay.
that diagonal multiplication trick.
Oh, okay. You created.
And
Okay. Go
I
ahead.
got 2304, but I also got 8 when plugging it into, so I don't really know.
Huh. Because 4 cubed. I mean, there's nothing we are doing wrong. So you created like a lower triangular matrix.
No, it joined the matrix with the first 2 columns
Uh-huh.
to make a 3 by 5 matrix out of the 140, 3, negative 2, 2, 5, 4, 5, 1, negative 1.
Okay. And so that will change. So what was the matrix that you got?
Um, I forget which section this was in. This was just a rule for finding the determinant of a 3 by 3 matrix that you can use.
Oh, okay, sure. Um, oh, I see. I see. So this is what you did. You go 1, 3, 4, 4, negative 2, 5, 0, 2, negative 1.
And then 1, 3, 4,
Yeah,
4, negative 2, 5.
but I'm surprised because it's got to come out to be the same. So you
Yeah.
multiply these, you get 2. 8 by 4, 32, 3 times, that's 0. And then you add these.
You
So,
add those, and then the top it was 0, 10, negative 12.
so this is negative 12 in this direction.
So it's 34 minus
And then that's
uh
10.
plus 2.
That's 0. So that's right, 34 minus 2. So that's 36. And then 4 cubed times that.
Times 36, which is 2304.
Right. But I'm wondering why the software is not given the same determinant for this.
Mm-hmm.
Let me go back because you're absolutely right. By the way, that's what it should be. So let's see if we can figure out what the software is doing. You can still, let me make sure. Stop share and share. I'm showing, there you go. Now again, unless I'm putting a number wrong, correct me if I'm wrong. This is the correct answer right now, 2,304. Let's clear this one. And I'm going to put the matrix that we just found using the method that you said. I'm just going to give this software another chance. 1, 4, 0, 3, -2, 2, 4, 5, -1. The inputs, they look correct, right? Nothing looks bad. And here's determinant. Oh, 36. So go figure. So 36 is right. So this is going to be 4 times. So it's going to be 64 times 36. Yeah, I don't know why the software did not give that number to us the first time. I don't think I put it in correctly. But anyway, thank you so much for that. So we're good now, I think, right? No biggie, no problem. We figured it out. And okay, fantastic. So let me now. So we're good on this one, everybody. Let's change my share, go back to the page of the book. And oh, somebody asked, what is it with the 3x5 matrix? Okay, someone asked, what is the 3x5 matrix you mentioned? The reference to 3x5. Let me switch to my notepad and I show you what he meant. Again, the question is, what do you mean by 3x5 matrix? This is the 3x5 matrix that he was referencing. And this was the shortcut for finding the determinant of a 3x3. So remember, our matrix we want to find the determinant for was this matrix, right? 1, 4, 0, 3, -2, 2, 4, 5, -1. You replicate the first two columns, and that's how you get 3x5 matrix. So that's just the shortcut method. You can do it this way. You multiply numbers in the diagonal here. 1 by -2 by -2 is 2. 4, 2, 4, the product 32. 0, 3, 5, the product 0. And then you're going to add these numbers. Okay. And then we look at product going in the other direction. -12, this one 1, 2, 5, 10. 0, -2, 4 is 0. You add these numbers. And then the sum 32 and 2, that's 34. And then you subtract the sum of these numbers going in the other direction, which is -2, so you get 36. Again, this is the 3x5 he was referencing. Okay. Now, let's go back to the book and let's try the example in the book. And again, you're welcome. Again, feel free to call out any problems you like, but I'm trying to do ones that are similar to your homework problems. Okay, having done number 10, the rest of them are okay. Let's take a look at, for instance, number something simple, number 20, for instance. There you go, number 20. So in number 20, the question reads, use a determinant to decide whether the matrix is singular or non-singular. So in number 20, the matrix is, call it A. So what do you think we have to do, by the way, folks, to determine, being in the section on determinant, what determines that this matrix is singular or not?
Whether the determinant is 0 or not.
Perfect. Thank you very much. So exactly, indeed. So let's find the determinant of this matrix. And for the determinant, again, you can use the software. In fact, without going to the software, switch in my view, I'm just going to go and do this. I am on that matrix calculator, just so if you wonder what I'm doing. I'm inputting the elements here of the matrix 1, 0, 4. Again, I'm on that matrix calculator website. And then I have 0, 6, 3, And I have 2, -1, 4, 2, -1, 4. And then determinant. The determinant turns out, let me see. Oh, it's 1, 0, 4. Sorry, I put 3. 1, 0, 4, right? 0, 6, 3. Oh, good thing I double checked. Determinant. The determinant is -21. There. -21, and it is different from 0. 0 is the magic number here. So because it's not 0, therefore A is non-singular. That's all this one asked for. Okay. And we have that one. Let me now switch to the book again. And, okay. Following number 10. And again, if you have questions, please ask. Now, let's do number 26. Right in this segment, number 26, right in here. In number 26, the question reads, find the determinant of A inverse. Okay. Now, it says begin by finding A inverse and then evaluate its determinant. So I'm just going to copy number 26. And I know it's a 2 by 2. Well, let's do 28 because it's 3 by 3. 2 by 2s are easy. So let's do 28. In 28, matrix A is 1, 2, 1. And then 0, -1, -2, 1, 2, 3. So that's matrix A. Again, it says begin by finding A inverse. So I need to find the inverse of this matrix. And then evaluate its determinant. I will go to that site and find its inverse and its determinant. And I'll show you again what I'm doing in a moment in my notepad. I'm just copying information from the problem. And then it reads, verify your results by finding the determinant of A. So I need to find determinant of A. And then applying the formula that determinant of A inverse is equal to 1 over the determinant of A. Okay, so let's do that. Let us switch to stop share. And I'm going to go to the website again and do this. Okay. So first I need to find the inverse of the matrix, right? Let's clear this. So I'm going to put that 3 by 3. The numbers are 1 tab, 0, 1 tab, 101, 2, -1, 2, 2, -1, 2, and 1, -2, 3. Okay. It says find the inverse, and here's the inverse. Okay, so this is the inverse of the matrix. I'm going to copy that inverse. The inverse turns out to be -1/2, 1, -1/2. Second row, 2, -1, 0. And the third row is 3/2, -1, and 1/2. Okay. And then it says find the determinant of that. So let me clear this and input this. Oh, actually, I just realized to the right in here, folks, see, this is the inverse, right? To the right, it says insert in A, insert in B. Perfect, I'm going to do that. Let's insert in A. Ah, isn't that great? I don't have to type these in. They're all up here. And then let's find the determinant. The determinant is -1/2. Okay. Now, let's find determinant of A. Let me see. Inverse. If I get inverse of the inverse, I get the same matrix back, right? So instead of me typing it in, I got inverse of the inverse. Now I'm going to insert that in A. There you go. Now I don't have to type them in. All right. Now let's find the determinant of this just a straight A without the inverse. That determinant is -2. Now let me switch to my notepad and I show you what I'm doing on the notepad. All right. So this is what I have so far. Number 28. Here's matrix A. We found the inverse. The determinant of the inverse is negative a half. And then the determinant of A itself is negative 2. The problem said verify this property. So the determinant of A inverse is going to be 1 over the determinant of A, which is negative 2. And of course, that's negative a half. And these are equivalent statements. They end up being the same. So it works. That's good. We simply verified it. Everyone okay on this work so far? All right, let's go back to the text and we're just going to do one more here and then we go on to chapter 4. Let's see, let me share the book. Share our book right here. And this time we're going to go further south. Let's take a look at exercise number 40. In number 40, it says find the determinant of A transpose, A squared, AA transpose, 2A, and determinant of A inverse. Now, we're going to do all of these, A through E, simply by using the determinant of A. Let's see how this is going to work out. First, let me copy the problem. Exercise number 40, determinant of A. Now, to find the determinant, I'm going to use again the software. And you're welcome, by the way, to use the software during the exam too, because I've been using it ever since week number 2. And then 4, 2, negative 3. All right. Now I'm going to switch to my notepad and then let's see how we're going to do this. Stop share and my notepad. All right. Now I'm reading from the book, folks. In part A, it says, find the determinant of A transpose. What do you think the determinant of A transpose would be?
It's equal to that of A.
Perfect. Thank you. Determinant of A. Remember, we had a theorem that said determinant of A transpose and determinant of A are the same. Oh, determinant of A, I did, by the way, I got 18, that one. So the A transpose, it's going to be, its determinant is 18. In part B, what is the determinant of A squared? We're supposed to use the properties of determinants in this one. So how do you think, if I have determinant of A, which I do up here, how would I use that to find A squared? Can I square it? Let's see. Determinant of A squared means determinant of A times A. And the product of determinant, the determinant of a product is product of determinants. So that's del A times determinant of A. All right. And this one, 18 squared. And 18 squared is, it looks like 324 there. All right. In part C, we were supposed to find the determinant of A times A transpose. How do you think we should do that one?
It's equal to the determinant of A squared.
Perfect. Because determinant of A transpose and A are the same, so that's exactly the same as determinant of A squared, and we just found it. The answer to this is also 324. Thank you. And let's check out part D of this one, just a couple of more parts. In part D, determinant of 2a twice a. Now this is a little tricky. How do you think we're going to find determinant of 2a? If we know determinant of a.
It's 2 cubed times 18.
Beautiful. Good job. Remember, a constant multiple of 8. Let's go back here. There you go. This is what we're using. If you have a constant multiple of A, you do constant to the power of the order of the matrix. The constant in number 40 here is 2. And the order is 3. This is a 3 by 3. So you go 2 cubed determinant of A, and 2 cubed is, of course, 8 times determinant of A is 18. And that would be what, 144, 60, and 80, yep, 144. And finally, the last part of this, in part E, we have the determinant of A inverse. Could I do that without finding the inverse matrix? Determinant of A inverse. Remember, we did it, I think, up here. Yeah, it's directly above us. It's right here. There you have it. The determinant of A inverse is 1 over determinant of A. And that's just going to be 1 over 18. And there you have that. So really quickly, with just knowing determinant of one matrix A, we can do all of these other good stuff. So hopefully everybody's okay on this one. So that's what we didn't get to do last week. Now we are pretty much done with chapter 3. Don't worry about the last section, by the way, folks, in chapter 3, which is section 3.4. It's application using Cramer's method. Cramer's method involves determinants. I mean, I can just tell you about it without actually going through it. Let me share. Okay, so this is what I mean. The application Cramer's rule. Cramer's rule is like the quadratic formula for solving quadratic equations. It is a formula. It just gives you the answer. See, the solution to x1 is, the solution to x2 is. There. Gives you the solution. And you just find these determinants. And that's how it works. So you're welcome to look at this if you like on your own. I want to skip this one and go to chapter 4, actually. So everyone, hopefully you feel okay about determinants, what we've done. Okay, thank you. Fantastic. Now, let's begin then chapter 4. Now, in chapter 4, we're going to talk about vector spaces. So let me share my notepad. So we're going to talk about vector spaces. So the question is, what is a vector space? As the name implies, a vector space is like a space where all the vectors are in. They reside in that space. So we got a space with every vector you can imagine in it, all kinds of vectors. Now, first, let's define what we mean by a vector. And this you may have seen, by the way, in your pre-calculus or third semester calculus. And by the way, just if anybody could chime in here, any of you or all of you had Calc 2 and Calc 3 or just Calc 2?
Up
I
to
did
Calc
both.
4.
Calc 3? Okay, I've taken Calc 3. Okay, so because I think the prereq for the course is Calc 3, something like that. Not that we're going to do a lot of Calc 3 at all, but I thought because we're going to talk about something here. Okay, Guy. So taken up to Calc 4. Okay, so that Calc, then you were probably somebody that within they've taken up to Calc 4. So they were probably in the quarter system. Okay, good. So Calc 3 semester system, Calc 4. Then you've seen vectors. My point being that you've seen vectors in there in that course, minimum, if not in pre-calc. So we're going to call vector simply a directed line segment. A directed line segment. And it has both, being a directed line segment, well, it has both direction and magnitude, right? So those are the two attributes, magnitude of every vector. It has a direction and it has a magnitude. Now, we're going to use like lowercase x, u, v, w, pretty much the standard. Your book uses the same letters for the vectors. A vector, the graph of a vector in R2, that means in 2 dimension. Here's our XY coordinate system, and here's my directed line segment. This is what we call a position vector because it starts at 0, 0. So this point is the initial point of the vector, and of course, where it stops is going to be the terminal point. So you always have a start, an initial, and a terminal point. Okay. Now, the coordinates of the point as a point is going to be x1, x2, and here's vector x. Now, in the book, and you'll see in a moment, in the book, they use boldface for vector quantities. I'm sure you're familiar with that. So for instance, if I have a vector u, and I'm going to make it boldface, so this is how it would look like in the book. You see that bold U? That's exactly the same as our U that's not bold with an arrow on top. Now, in classrooms, in our notes, just about everyone in the world does what I'm doing because we don't want to be spending time trying to boldface and these letters and stuff. So we just take the easy way out. We put an arrow on top, meaning that's a vector quantity. Now, the notation that your book uses for vector x. So here's vector x in Larson. He actually uses x1 comma x2, just like coordinates of the point R. So this is his notation for the vector. But and I use his notation as much as we can because we're using the book. But don't be surprised if later on we write it like this, or as we go through, I may switch to the angled brackets. This one is more universal way of showing the vectors. Okay, now because there's only two components here, this vector that you're looking at is in R, that funny looking R. That means real space. So we are in real space and R2. So we have a two-dimensional, if you will, space. Now, when we think of a space, we think about 3 dimension, right? So it's really a two-dimensional plane that we're looking at. And R means we're looking at the real plane. And the 3-dimensional version of this would be R cubed. And of course, this theoretically can go to Rn. We could have n-dimensional real space. So I could have R4, R5, and so on and so forth. Okay. Now, suppose I have two vectors. Let's call them U and V. Okay. Two vectors, U and V. We're going to say they're equal if and only if their components are exactly the same. U1 and V1. U2 equals V2. Now notice, by the way, the U1, U2, V1, V2, they don't have arrows. The components are real, just like they are here with x's. And here's what I'm thinking. Vector U is made up of U1, U2. vector v1 is made up of components v1, v2. So there you go. In order for u and v to be equal means identical, the components must be identical also, the corresponding components. Then we talked about vector addition. How do we add vectors? Their addition, which is u plus v. The vector addition, you actually add the components u1 and v1, comma, u2 plus v2. So those would be the components. Now to add vectors, we'll see if he asks us in the exercises to do it. We're not going to do this geometrically, but to add vectors, you've seen them, right? We use parallelogram. Let me just write them. The geometrical method of adding them. We use what? Triangular method. And we can also do parallelogram method of adding these vectors. So for instance, let's say this is vector u and this is vector v. And I want to add those two vectors. If I do the parallelogram method, in parallelogram method, I'm going to draw a vector that's same direction, same magnitude as u. So it's going to be this vector. That's going to be vector u. And then draw a vector that's same direction, same magnitude as v. And that's how we create a parallelogram. These two vectors, v and itself, parallel to itself. U parallel to itself. And then the sum vector is going to go from here, corner to corner. And there you have it. This would be the sum vector. This one, this vector is u plus v. And that is the parallelogram method. You create a parallelogram. The triangular method is kind of like half a parallelogram. If I want to do this using triangular method, here's vector u, and this is vector v, right? So what we do is the following. This is u, so you're going to draw a vector equivalent to vector u, same direction, same magnitude, so that's vector u. And then I'm going to connect from u to v, and let me use my ruler here so I draw straight. And there you go. So that's going to be the sum vector. That is vector u plus vector v. Okay, so that would be the triangular method. So for triangular method, what you do is you put the tail of vector, what you call it, vector u, it touches the tip of vector v, right? When you translate it. And then the sum vector, it's going to go from tail of v to the tip of u. So tail, tip. For that reason, we often call this the tail to tip method of adding vectors. Tail to tip method. Okay. So however you do it, that's geometrically how it's done. Again, we're not going to do a lot of geometrical work with vectors. We're going to work with a more analytical way of doing it. Okay, so everybody's good so far, I hope. We're okay, everyone?
Yes.
Okay, fantastic. Thank you. Now, let's talk about the zero vector. The zero, hold on. Let's talk about the zero vector. And a zero vector, it is what you would think it to be. It's a vector that has a magnitude of 0. And the arrow on top, that means it's a vector quantity. In R2, a zero vector looks like this. It has both x and y, or x1, x2. Both components are 0. Inside the angle brackets, by the way, the components, these are real numbers. This is a vector quantity, so please be mindful of that. This is a vector quantity where this and this one, these are real numbers. Call them scalars. You see that? Now, remember, every vector has a direction and a magnitude. So the magnitude of zero vector is 0. What do you think its direction is?
Mm,
Just a wild guess.
Nothing?
Pretty much, you're right. A zero vector, there you go. Here's my zero vector. See that? I just have an arrow tip. That means it's pointing north. Now, if you want to make it point to the right, you want to make it point left. If you want, make it point down. If you want, make it point any direction. These are all zero vectors. So the direction really doesn't matter. It really doesn't have anything. So it's arbitrary. Okay. Now, zero vectors, we work them again analytically. So don't worry, because nobody's going to ask you to graph a zero vector because it doesn't have magnitude. It's just the tip of an arrow. And the tip of an arrow can rotate any direction. All right. Now, next, let's talk about scalar multiplication. We are very selective, by the way, as far as the operation on the vectors here. We talked about addition and scalar multiplication. We're talking about just those two primarily for a reason that you will see shortly. So we're looking at scalar multiplication by C. Here, C, again, is a scalar. And in the world of vectors, a scalar means a constant. Now, what does a scalar multiplication look like? So I have C, and here's vector V arrow on top. And again, please be mindful of the arrow on top. If I forget to put it, please remind me, because without it, C and V are now both scalars. You see that? Without the arrow. So I do have CV as a vector, and that means C times the components of the vector. See, now I'm not putting arrows on V1, V2, because these are scalars. These are constants. And how is this scalar multiple going to work? You actually distribute this distributive property. You do CV1 and then CV2, and that would be the scalar multiple, they call it, of that vector V. So for example, whatever vector V is, if I do 5V, it's going to be 5 times the magnitude of vector V. Okay, so vector V, for example, is a unit vector, means length 1. 5 times V would be a vector of magnitude 5, length 5. Okay. So, and the reason it's called scalars, like why do they call them scalar? Why don't they call them constants? Let me put that. The reason it's called scalars because these scalars, like C, these actually, they change the quote unquote scale of vector V. They change the scale of it. And when you scale things, remember you like magnify them or zoom in, zoom out. That's what scaling does to an image. So that's what is called scalar. They scale vector V. So 2V would scale it twice the size. So it's going to be 2 times V. Now, if if C is positive, what do you think the direction of, for instance, suppose I have, this is vector V here, and I want to do half V, 1/2 V. What do you think the direction of vector half V be? I know the magnitude will be half as long, so let me draw that. That's halfway mark. Now, will the arrow point in the same direction or opposite direction? For half.
Same.
Same, thank you. There you go. So if C is positive, then let's say CV has same direction. Same direction as vector v. It's just half the size. So what is negative 1v therefore going to look like? This time c is less than 0. If c is less than 0, the negative will change the direction now, doesn't it? So whether c is positive or negative, that attributes to the direction of the vector. So c less than 0, then we will have opposite direction. Opposite direction. Okay. So this vector is negative 1v. Exactly same magnitude as v. Like if this is an inch long, that would be an inch long also, only going to the opposite direction. Okay. Now, the fact that we have this positive and negative scalars enable us to define matrix differences now. So if you want to find the difference of a matrix, that would be u minus v. Just like with numbers, remember subtraction is defined in terms of addition with opposites. So we can say, well, instead of subtracting vector v, I'm going to add negative of v to u. It's because I know this vector does exist, right? Scalar multiple. So we are adding this way. And that's how we subtract vectors. You add opposite of the second vector. Now, subtraction is not commutative. So u minus v, v minus u would be different. So everybody okay on this work? Fantastic. So let me move this. Now I'm going to switch to the book here so you don't have to write all of these. We're almost done with section 1, by the way. But let me switch to the book so it'll go a little faster. Okay, again, everybody hopefully is okay. If not, please ask questions. Let me see in the chat. Oh, everything is good. All right. Again, thank you for responding in the chat, everyone, about the calculus. Cool. Now, let's go to, we talked about determinants and, okay. So vector spaces, that's what we're doing right now. We are in section 4.1. We're looking at vectors in Rn. Again, that means an n-dimensional space of real numbers, real vectors. Okay, so in section 1, we just talked about these notions. We talked about how to add, subtract vectors, the addition using parallelogram method. You can actually analytically add vectors too. I mentioned that. You add the components of the vector. This would be the scalar multiple of the vector. So here's v shooting in this direction. For positive c, the vector cv scalar multiple will go in the same direction, and its magnitude would be whatever c is positive. So it could be like if it's 2v, would be twice the magnitude and what have you. Now, theorem 4.1, there you go. So we got these 10 properties of vector addition and scalar multiplication. Okay, now the first 5 are vector additions. The last 5, that's numbers 6 through 10. These are scalar multiplication by a vector. Now, and all of these pretty much act or behave the way you would expect them to. So, for instance, number 1, when you add u plus v, that's going to be a vector in the plane. And u plus v is a vector in the plane. Oh, let me go back up here. Sorry. Notice, by the way, boldface, just about everything is boldface, right? So boldface u, that means this is vector. Boldface v, vector. boldface W vector. The books don't use arrow on top because they have the luxury of bold-facing stuff. Now, the closure under addition. In the right, it's good description that we see here explains what it means, the one on the left. So when the problem shows, or for instance, in a homework, he may ask, show that vector V and W are closed under addition. That means we need to show U plus V is a vector. It's very simple. Now, this is the number 2 is the commutative law, commutative property of addition. You can add vectors in any order, okay? Number 3 is the associative property. All these properties, by the way, folks, we have them with numbers, don't we? In R1, with numbers, we can add 2 numbers. The result would be another number. That's the closure for R1. 2 plus 5, 5 plus 2. That's the commutative property of addition with numbers. So it works with vectors. Everything we do in R1, that means just with basic numbers, are subset of operations that we can do in the vector space, by the way. And that's pretty cool. Now, the associative property allows us to change the order of addition, right? Just like it does with numbers. Number 4 is the familiar additive identity. Any vector plus the 0 vector gives you the vector itself. Okay, so 0 here is the additive identity element. Number 5, the last one for vector addition is your additive inverse property of vectors. Any vector plus its opposite give you the 0 vector. So the first 5 are again addition property of vectors. The last 5 are scalar multiplication. So number 6, C. C is a scalar here, right? It's a constant. Cu is a vector in the plane. So this is the closure under scalar multiplication. What Cu tells us, the closure is this. If you multiply any vector times any constant you please to, you're guaranteed that there's going to be a vector that will be able to match this. So for example, again, if I have a vector U is 1, 2 coordinates, and I multiply 1, 2 components, 1, 2 by 1,000, is there going to be a matrix? I'm sorry, is there going to be a vector that's going to exist? It's going to be that? Yes, we're guaranteed that Cu will also be a vector in the plane. So pretty much you're not going to run out of vectors. Any vector you create is going to belong to the plane. The distributive property, remember C is a constant scalar. C times the sum of 2 vectors, you can distribute C to U and distribute C to V. Number 8, you add 2 scalars times the vector. You can distribute each scalar to the vector and add them. Okay, and number 9 is the associative property of multiplication. CDU equals CDU. Now he's changing the order of multiplication of a scalar. Right now, number 9, I have highlighted DU. Well, maybe I don't like to like DU. Let's say C is 2/3. D is 3/2. Why do I want to multiply 3/2 times U, create a bunch of fractions? Why don't I multiply 2/3? That's my made up number. C times D 3/2. The reciprocals are 1, so this is where it may come in handy. And finally, we have multiplicative identity. Remember, the additive identity is the 0 vector. The multiplicative identity says 1 times any vector gives you the vector itself. So those together make up the properties of vector addition, scalar multiplication. Everyone okay on these properties, I hope? We're good. Okay. Now, now that we have seen these, so this is, remember, this is in plane, by the way. We're looking at R2. Everything that you just saw, observed, is in R2. And the proof of these, by the way, if you're interested, the proofs are, some of them are here. Some of the proofs are in the exercises, but again, these are pretty trivial. So you could look at the proofs if you like to. Now, coming out of vectors in R2, meaning in the plane, what about in space, R3, or in general, Rn? Now, geometrically, we can only go to 3-dimension, right? When we graph things. So R3, we can still graph these vectors in 3-dimension in space. But then theoretically, we could have a vector in 4-dimension, in n-dimension. So R1, he says that's 1 space, 2 space, 3 space, and 4 space, and so on, all the way up to n space. Again, of course, visually beyond 3, we don't visualize these, but theoretically they exist. The ordered, in the case of plane vectors, we have ordered pairs, right? X1, X2. In the case of R3, we have ordered triples, X1, X2, X3. And then in general, we call those ordered n-tuple. The n-tuples, so for instance, the ordered triple here, that's what this is, 1, 2, 3. The n-tuple you see here for x1 through xn, that is the ordered n-tuple. Order is important here, folks. Just like in 2-dimensional case, remember we call those pairs ordered pairs? So these are ordered n-tuples. So if you switch x2, x1, you get a different point in space. All right. Now, this is now definition of vector addition, scalar multiplication in Rn. Instead of plane, it's very similar. In fact, the addition, scalar multiplication in R2 is a special case of this one. So here's vector u, the n-tuple, u1, u2, all the way up to un, vector v, v1, all the way up to vn. What if you want to sum the vectors? If you want to find the sum vector, u plus v, you just add the component of each of those, u1, v1, u2, v2, and so forth, all the way up to un, vn. So you add like components. When we do scalar multiplication of c, a constant, by a vector, you distribute the constant to every component of the vector. So 3u would be 3u1, 3u2, 3u3, and so forth. Okay. The negative, remember the negative, so you just change sign on the components, turn each of those to their opposites, and then we can define the difference that way. Okay, so hopefully everybody's good in this one. Now look at the zero vector, by the way, in Rn. Again, it's extension of the 2-dimensional version, right? In R2, we have 0, 0. In R3, we have 0, 0, 0. And in Rn, we have n zeros ordered. Of course, 0, 0 order here. If we become careless, we can get away with it just with a zero vector, because zeros are not distinguishable. All right. Hopefully, again, everybody is still good. Now, those 10 properties that we saw earlier that I went over, so I'm not going to go over this because you've seen this before. The difference now, everything we did in R2, there you go, it works in Rn. So all 10 of those, the first 5, addition, vector addition, and the latter 5 are scalar multiplications. Okay. Now, the sum, and the scalar multiplication, folks, they call these, quote unquote, standard. These are standard operations in Rn. So we have two standard operations, addition and scalar multiplication. Okay. We could define non-standard operations. We'll look at those later. But standard operations are addition and scalar multiplication. So these standard operations are going to be, again, u plus v. And let me go back up here. Sorry. There you go. These are the standard operation in Rn. Vector addition and scalar multiplication. We're going to call these standard operations. And it's right up here. See, I overlooked that. Those are the standard operations. Other operations would be tagged as non-standard. And we saw properties of standard operations, or properties of vectors, vector addition and scalar multiplication. That's theorem 4.2. Okay. Now these are pretty much, actually, these are also called axioms or definitions of operation in Rn. Now, let's see what else. Now we're going to look at properties of additive identity and additive inverse. Remember the additive identity, that would be 0, right? So, so we have a vector in Rn and a scalar. So the additive identity is unique. That's the theorem. It says the additive identity is unique. In other words, right here, u has to be 0. If v plus u equals v, then u must be 0. The additive inverse is unique. That means if v plus u gives you the 0 vector, then u must be opposite of v so that they add to 0. That's the only way this could happen. If u and v are opposites, they add to 0. Number 3, 0v equals 0. Now here you got to be careful. Remember the first 0 doesn't have arrows, so that's a scalar. The 0 to the right is a vector quantity because it's in boldface. So scalar 0 times any vector turns that vector into a 0 vector. That's property number 3. Number 4, scalar c times 0 vector doesn't do anything to the 0 vector. So in other words, any scalar multiple of 0 is 0 vector. Number 5, c is a scalar, v is a vector. If the product of c, scalar c times vector v is 0, then two things must follow. Either the scalar is 0, so that 0v becomes 0, that's item 3. Either c is 0 to make that happen, or if c is not 0, then vector v must be 0, so property number 4 holds. You see that one? So the consequence of 3 and 4, we can prove this one actually. So again, think of it as 0 factor principle for scalar multiplication equals 0. Constant must be 0, scalar, or v must be a 0 vector. And number 6, double negative rule. Negative of negative gives you positive. So opposite of an opposite gives you positive v. Hopefully everybody's still okay on this work. All right. Now let's see what else. Almost done with this. Okay, let's talk about linear combination of vectors. And there you go. When we say we can write a vector as a linear combination of other vectors, it really means this. If you add scalar multiple of one vector to scalar multiple of another vector, and so on, as many vectors as it takes, and that gives you vector x, then we say x is written as a linear combination of the sum of these other vectors. So that's what the linear combination is. X is a linear combination of vectors v1, v2, and so forth. Now, some linear combinations are obvious. You can see, oh yeah, vector X is when you add these two vectors. Some of them are not so easy to see. Okay, we'll do an example. We'll see in a moment how this works. And that's pretty much it in this section. We're done. Good. We've reached the exercises, which is a good stopping point here, folks, because let's see. We can actually now take a break, huh? So let me pause the recording here because we've reached our breaking time here. Let me pause. All right, so let's take a look at these exercises. Again, I'm looking at section 4.1, something similar to your homework problem. So let's take a look at exercise number 10. Again, some of these are fairly simple, straightforward. I just want to touch up on a little bit of everything here. So let's begin with exercise number 10. In exercise number 10, finding the sum of two vectors. This says find the sum of vectors and illustrate the sum geometrically. Okay, so let's do that. I'm going to copy these so I show you the work I do on paper. Let me change my share. And here we go. So this is again section 4.1. And we're going to look at exercise number 10. In exercise number 10, we have a vector in R2, and the components are 2, -3, and the other vector, vector V, its components are -3, -1. Okay. Now, let's see, the sum vector. So what will the sum vector be, right? Because that's what the question asked for. Let me check, make sure real quick. Yeah, in number 10, the question says, find the sum of the vectors in number 10. Actually, hold on. This is number 9 I'm doing. Sorry, this is number 9. I'm doing number 9 here. Okay, in number 9, so the vector is 2, -3, vector V is -3, -1. Now let's do U plus V. Remember, for the sum vector, we add the components, like components, so that's 2 plus -3, comma, -3 plus -1. And the sum vector is going to be, what, -1, right? Yeah, it's going to be -1, comma, -4. That's going to be number 9, right? And again, if you have questions, by all means, feel free to ask questions. Now, we need to graph these, correct? So let's see how we're going to graph them. First, we're going to graph individually. Let's graph each of them. And hold on. Okay. Let's do this. So here is, we're going to look at U plus V, right? Let me, sorry if I'm doing this. I want to make sure you can see. Okay, my note. All right, so we're going to do U plus V. So vector U now is 2, comma, -3. So it's just like X is positive, Y negative, right? So that vector is going to be located, and these are all position vectors. So they start at 0, 0, correct? They start at 0, 0. So 2, negative 3, x is positive, y is negative, right? So that means if I graph that one, that's going to be in the fourth quadrant, right? 1, 2, 1, 2, 3. So that's going to be this vector. That's vector u. This is vector u. And here's x, and there's y. Vector v is negative 3, negative 1. So that's going to be in the third quadrant. This is like 1, 2, 3, and negative 1 would be here. And that would be vector v. Now the sum vector is negative 1, negative 4. This is negative 1, 1, 2, 3, and negative 4, roughly about here. So this is where the sum vector is going to go. There. That's going to be u plus v. And this is analytical method of doing it. We did not use triangle or parallelogram to do it. We simply use analytical method using numbers and properties. Okay. But if we did do the parallelogram, for example, this would be equivalent to vector u, right? And this would be equivalent to vector v. It would go this way, u goes this way, and there's the diagonal of the parallelogram. So pretty simple, straightforward, I hope. Let's take a look at another one. And again, unless you ask, I gather everybody's okay on the examples we're doing. So let's go back to the book now. What happened to my book? I somehow managed to get rid of my book. Hold on, folks. Share. And yeah, let me, I don't know what happened to my book here. Sorry, folks, hold on. Okay. I don't know what happened, but I got it back. Sorry about that, everyone. There it is. For some reason, the book just closed on me. No worries. So we're in section 4.1 exercises. There you have it. Let's take a look at number 22 in some looking at vector operations, looking at this segment. Now, in exercise number 22, the question, you're given two vectors. Let me write this, number 22. Vector u is 1, 2, 3. And vector v is going to be 2, 2, negative 1. And vector w is 4, 0, negative 4. Okay. And the question reads, find number 22, find 5u negative 3v and negative 1/2 w. So we're going to do exactly what the question is asking. Let me change my share to my notepad. Okay, so what I need to do is I need to first find 5u. So that means 5 times every element, every component of u. So the vector 5u is going to be 5, 10, 15. Now, negative 3v, that's going to be plus negative 3 times v. This is v, 2, 2, negative 1. Negative 3 times each component. So that's going to be negative 6, and 3. Okay, that's negative 3v. And then negative 1/2, that's going to be plus negative 1/2 times w. So you're going to divide everything by 2 for w. That's going to be by negative 2. So it's going to be negative 2, 0, and 2, right? To multiply by negative a half is to divide by negative 2. Good. And then we combine the components. So 5, negative 6, and negative 2, that's going to be negative 3. 10, negative 6, 0, that's going to give me 4. The last number is going to be 15, and 3 and 2, that makes up 20. So that's going to be the resultant vector. That's what that's going to be. Okay, let's go and do another one. This time, let's try. Again, if you want me to do any of them, please call it out. Otherwise, I'm just trying to get as close to your homework problems as possible. Let's take a look at number 28, top of the page here. In exercise number 28, the question reads, which of the following vectors are scalar multiples of z? Now, vector z here is given by 1/2, comma, negative 2/3, comma, 3/4. That's vector z. And let's take a look at vector u. U is 6, 4, 6, negative 4, 9. So how do you think? We're going to go, let's see, it says, which of the following are scalar multiples? So what do I need to do here? This is part A, and put next to that part B. Vector V is negative 1, 4/3, negative 3/2. So I'm just wondering, what is it that I'm supposed to be doing in here? If one is a scalar multiple of the other, then what can we say about, in part A, about u and z? If u is a scalar multiple of z, anyone want to take a gander at this one? What should be true about these two vectors, u and z?
That there should be a scalar that you could multiply z by to get u.
Perfect. Exactly. Thank you, Angel. So the scalar is c. So as you mentioned, we should be able to write u as a scalar multiple of z, right? C times z. Perfect. Now, let's see if that's possible. So here are the elements of u. They are 6, negative 4, 9. We're going to set it equal to c, and the elements of z are 1/2, negative 2/3, and 3/4. So if we can find such c, then u is a scalar multiple of z. Now, c times a vector z, every component is multiplied by c. It's like you distribute c to the components. So that means for the two vectors to be equal, remember the like components must be equal. Therefore, 6 equal c times 1/2 should equal to 6. Now, c times 1/2, multiply both sides by 2, that means c is 12. That's matching the first components. Let's match the second component. Second components are negative 4 for u, and z, the second component, is negative 2/3. Now remember, c is the same constant that multiplies by all three components. We don't have separate constant for each of them. It's got to be the same constant that distributes to every one of them. So let's solve this one now, this equation for c. To solve that one for c, how are we going to do this one? We're going to isolate c. So let's multiply both sides by the reciprocal of negative 2/3, which is 3/2 negative. So on the right side, I just get C. On the left, I'm multiplying by 3/2. So that's going to be 3 times 4, 12/2, 6. So C is going to be 6. And if you try it right here, I could stop, but just to kind of show you the other part of that, you say 9 equals C times 3/4. Now multiply both sides by reciprocal of the fraction, 4/3. 4/3, so that's going to be 4 times 9, 36/3, then that's 12, right? C would be 12. Yeah, 36/3, yeah, 12. So notice we got 12 for 2 of the components, but the middle one, unless I made a mistake, the middle one turned out to be 6. Therefore, the answer is it is not, right? We can say that U is not, because I'm going to say since U cannot be written as a constant multiple of Z, right? Therefore, it is not a scalar multiple of Z, a constant multiple of vector C. And there you go. That's how you would do that one. Now let's do the same thing for part B. Again, if V now is a constant multiple of Z, same thing holds. So we should be able to write V this time as C times C. Vector V, -1, 4/3, -3/2, equal C times Z, which is a half, -2/3 and 3/4. Now match the components. X component of V equals the X component of CZ. So from this, multiply both sides by 2. C is -2. The second components, we have 4/3 equated with C times -2/3. And to isolate C, I multiply both sides by reciprocal. That's -3/2 on both sides. So C would be -2 again, right? -3/2 times 2/3, negative is positive. -3/2, the 3 cancels, 4/2, -2. That looks right. And finally, -3/2, that's Z, scalar multiple, C times 3/4. Multiply both sides by reciprocal of 3/4, 4/3. And I'm doing this times 4/3. The 3's cancel, 4/2 is -2. Aha. Check this one out. Same. So for this one, yes, we can say vector V is -2 times Z, correct? So the scalar is -2. So therefore, V is a scalar multiple of Z. It is a scalar multiple of Z. And again, more specifically, it's -2 times Z. So that's what we mean by scalar multiples. Everyone good on that one, I hope? Any questions about exercise number 28? Again, ladies and gentlemen. No question. Okay, if no question, then let's take a look at the exercise. The next exercise, I was going to look at something a little different. For instance, let's go all the way to number 48, and then we'll be done with this section. Exercise number 48, this segment. This one, writing a linear combination. So this segment, the question reads, write vector V as a linear combination of these other 3 vectors. And this is what I was saying. Sometimes it's not obvious what the linear combination is. So if you look at number 48 here, there you go, this one. It's hard for me to see by inspection, visually, what linear combination of U1, U2, U3 gives me V? But let's go through the process and do this. So I'm going to, copy the problem down first of all. This problem number 48 is what we're doing. This is section 4.1. Number 48. In number 48, vector V is given by 2, 5, -4, 0. Vector U1 is 1, 3, 2, 1. Vector U2, the second vector, is 2, -2, -5, 4. And finally, U3 is 2, -1, 3, 6. So we have an ordered 4, because this is in R4. So we have ordered 4 tuples. Okay, so we're doing this in R4. Now let me switch to, sorry, let's switch to my notepad. Okay, so I went ahead and copied these. Let's see. Now, because we want to write vector V as a linear combination of the others, so this is what that means. I have to go a scalar multiple of U1. You can go C1, C2, C3, by the way. I'm just going to go A, B, C, plus B, U2, plus C, U3. This is what we mean by a linear combination of the 3 vectors. This should yield a vector V, right? It should give you that vector. If we can do this, then that's good. We should be able to do that. Now, A times U1, so what is this going to look like? And you can imagine what this is going to look like. When you multiply A times U1, B times U2, C U3 equal V, each of these components of U1, U2, U3, let's say the first components. The first component is going to be what? It's going to be A times 1. The first component of U2, B times U2 is going to be B times -2. And the component of CU3, it's going to be C, first component, C times 2, 2C. That should equal the first component of vector V, which is 2, right? So in other words, this is what I mean. A times 1, so that's A, plus B times 2, the first component of U2, that's 2B, plus CU3, first component is 2, 2 times C, that's going to be 2C. The sum of these should equal to the first component of vector V, and that's 2. That's my first equation. Now, what do you think? What do you think the second equation is going to be? Looks like I have A, B, C, so I'm preparing for 3 equations, 3 unknowns. Anyone, or actually it's going to be 4, sorry, because I have a 4 tuple, right? So it's going to be 4 equations, but only 3 unknowns, because you only have A, B, C. So one of the equation will be redundant, and we'll see how that works. So anyone wants to take a stab at the second equation for the second components of U1, U2, U3, and V? What will the second equation look like? For the second component, it's going to be that's going to be second component of U1 is 3 times A. So it's going to be 3A. Second component of U, -2. B Second component of U3 is -1, C. That should equal second component of vector V, 5. Now you look at the third component, third of U1, third of U2, third of U3. Each of these multiplied by A, B, C respectively. So it's going to be 2A -5B plus 3C equals to -4. And finally, the fourth component, the -4 here is the third component of V. The fourth component of vector V is clearly 0, so that's 0. Now the fourth components of U1, 2, 3, 1 times A, so that's just A, plus 4B plus 6C, right, equals 0. Now, I need to solve this system, correct? So, how do you suggest we solve the system? Oh, first, before you suggest how we're going to do the system, any question on how I set up the system? Okay, so hopefully everyone's okay. Now, I need to actually solve a system here, true? So to solve a system, I'm in Symbol Lab now, right? So let's create a matrix. We're going to create the augmented matrix because I want to solve the system. This matrix is going to be for, let's see, the whole system, right? 1, 2, 3, 4. And it's going to be a 4 by 4, right? That's going to be the augmented matrix. One more, 4 by 4. Okay. The coefficients are 1, 2, 2, 2. Then we have 3, -2, -1, 5. I'm in Symbol Lab, folks. 2, -5, 3, and -4. And the last row is going to be 1, 4, 6, 0. Just let me check, make sure I transpose the numbers correctly. Transfer them. Yeah, it looks right, but please again, double check. Now, what are we doing? Oh, forgot. We're going to do Gauss-Jordan on this, right? So I hope this is going to work. Gauss-Jordan. I think if I just write that, it's going to do it. Gauss-Jordan, no, yeah, it did. Wow, I'll be darned. Okay, there you go. And here's the solution, by the way. Now look at this last row of this matrix. You see that 0, 0, 0, 0. What does that tell us? What does that mean when you have a row of zeros? This was a matrix for 3 equations, 4 equations, 3 unknowns. Remember, if you have more equations than unknowns, that means your equations are redundant, right? In this case, 3 unknowns, I need 3 independent equations. I had 4. So that means one of them is a linear combination of the other one. And that's what this last row indicates, right? 0, 0, 0, 0 means you had 1 redundant equation. So ignore that one and just look at the 3 by 4. Remember, the 1, 1, 1, these are the coefficients on A, B, and C. Therefore, we have the solution. The solution, I'm not copying the solution. The solution for this is going to be A, B, C. I'll show you in a moment what I'm writing down in my note. I'm just copying the answer. 2, 1, -1, correct? Isn't C -1? B is 1, and A is 2. And that's what we need. Let me switch back. And there you go. This is what I just copied from Symbol app. Therefore, we can write vector v. Remember, v is a linear combination of the other three. So that means vector v is a u1. A is 2. So if you go twice u1, vector u1 that is, plus 1 u2, that's just u2, negative u3. You should be able to get that vector. Does that make sense? Everyone okay on this work? We're good?
Yep.
Thank you, Angel. All right, so we're done with this section then. Let's go on to our next section, if everybody's okay. So let's embark on our next section. The section 4.2 would be vector spaces. Let me write that. Section 4.2, vector spaces. Now, let's switch to the book. And here's the book. All right, so what is a vector space? Let's actually talk about this one. So a vector space is any set that satisfies these 10 axioms, the 10 axioms that we saw in previous section, in section 4.1. Remember, we had the addition vector of vectors. The first 5 were addition. The latter 5 were scalar multiplication. There you go, scalar multiplication and addition. The standard operations. So any set that has these 10, we're going to call them axioms now. We call it a vector space. And the objects that are in this set, by the way, are vectors. Okay, so here is the definition of a vector space. So now this time, the book calls capital V. Notice it's not boldface. So this is the name of V for vector space. So here, let V be a set on which 2 operations, the standard operations, vector addition and scalar multiplications, are defined. If the listed axioms are satisfied for every vector in V and every scalar CD in V, then this defines a vector space. So again, it's important to know that a vector space V, according to the book, is a set on which 2 operations, see these 2 standard operations, these 2 operations are defined. Now, the 10 axioms, you've seen it already, so we can go through this rather quickly. So these are your closures. We've already seen that, except now we're more specific. The closure, if U is in V, vector V is in vector space V. Remember, he's choosing 2 vectors, only 2 vectors in that vector space. So if U and V are in V, so is their sum. And again, this guarantees that we're not going to run out of vectors. The closure, the sum of 2 vectors, we are guaranteed is going to be in the vector space. And and then you have the other ones, the commutative, associative, the 0 vector, additive identity is there. Additive inverse must be there. So every vector space must have an additive identity. That means 0. When 0 is in a vector space, we say the space is a non-empty space. So a non-empty space has the 0 vector in it, at least a 0, the trivial vector, if you will, must have that. At least that is in there, plus a whole bunch of others. The additive inverse should be there. That means for every vector you make up, negative of u, opposite of it should be there also, so that they create the zero vector. And remember, zero vector is going to be there because that's the additive identity. Good. Therefore, looking at what you see here, then we can, generally speaking, say that the vector space has four entities. The four entities are, you have a set of vectors, in this case, u and v. So you have a set of vectors, u, v, and here w, a set of vectors. That's the first identity. And then you have a set of scalars, such as c and d. So you have a set of, again, vectors, a set of scalars, and then you have two operations, addition, scalar multiplication, and those together form the vector space. Okay. Now your scalars here, by the way, c and d, are real numbers, and you can include scalar 0 in your numbers because 0 is a real number. Okay. Now, the set V here, the vector space for us, for instance, it's not going to be always quote unquote vector like the ones you've seen, components 1, 2, 3, 4, 5, like that. These vectors actually may be matrices. The components of them could be matrices. The vector spaces could be polynomial. It could be functions. So they could be anything really. So, and we'll see example of these in a moment. Again, if you have any questions, by all means ask. So here you go. This is a vector. Oh, let me look at the one above it here. This is the vector space for all 2x3 matrices. See that? 2x3 matrices. This is a vector space. So it's not a vector like we saw in R2. And this one, look at the vector space. This is all polynomial, degree 2 or less. In other words, these are all quadratic polynomials, right? This is the vector space for all quadratic polynomials. And we'll go do our own in just a moment. This is a vector space of continuous functions. If f is continuous, g is continuous. F plus g is in there, so it's closed under addition and closed under scalar multiplication. Therefore, this is a vector space, right? Because c times f of x, that is scalar multiplication of a function, exists. And there you go. Now, this is just a summary. It's not an exhaustive list. It's just, you just handpicked a few. So these are some vector spaces. All your real numbers that you've done up until this course, they form vector spaces because the set of real numbers is closed under addition. You're guaranteed when you add two numbers, the result, the sum will be in the set of real numbers. So for example, if I add 1,000 plus 2,000, will 3,000 be there? Yes, you're guaranteed by closure. The result of the sum of any two numbers will be in another real number. So every one of these, you can likewise think, these are all, they form vector space. That means all of these work, right? They work with those scalar multiplication, the 5 properties and the 5 additions. All of those hold for these vector spaces. Okay, so that's what that means. Now, hopefully everybody still okay here. All right, if everybody is good, let's continue on. Now, then we go on to our theorem 4.4. We're getting close to the exercises. Theorem 4.4 now looks at properties of scalar multiplication. Okay, these scalar multiplication, 0 scalar times any vector. Now we're looking at V as a vector that is element of the vector space V. So 0 times V gives you the 0 vector, just like before. If a scalar multiple times V is 0 vector, then either scalar is 0 or V is a 0 vector. All right, you've seen these before. Number 2, a scalar multiple of the 0 vector gives you 0 vector. -1 times V gives you negative of V. So these we've seen before. The proof of these again are in there. Some of them are in the exercises too. Let's see. I think that's all there is in this section, so that's good. We can actually go to our exercises and spend the rest of the evening on those exercises. Now, so remember, those 10 operations that we saw are required in order to have a vector space. So let's take a look at maybe one from each segment here I'll try to do. So in exercise, for instance, I don't know, number 4. This is number 4. The question reads, describe the 0 vector, which is called the additive identity. What does the 0 vector look like in number 4? M, remember, M is a matrix here. This is the set of all matrices that are 1 by 4. 1 means 1 row, 4 means 4 columns. So M14, what is the 0 vector gonna look like for this matrix? 1 row, 4 columns. One row, 4 columns.
Would it just be 4 zeros?
You got it. So M14 here, exactly. Just do a row matrix, 0, 0, 0, 0. There. That's going to be the setup again, all 1 by 4 matrices. That's what the 0 looks like. What about like number 5, P3? P3 means a set of all third-degree polynomials. Let me switch to my, let me write this and number 6, and then I switch to my notepad so you see how it's done. Number 6 is M2, 2. Again, we want to know what the 0 matrix looks like. So for the first one, again, everybody agrees that's going to be a row vector of 0, 0, 0, 0. Now, what about the set of all third-degree polynomials? What does the 0 vector look like? Now, P3 would be third-degree polynomials or less, right? So what is this going to look like? P3, again, that means degree is less than or equal 3. So if you have a quadratic expression, actually, it could also be thought of as a third-degree polynomial, but the coefficient is 0. So what does this 0 vector look like for number 5? Remember your polynomial P3. Let's write that. What does P3 looks like? P3 is this way. AX cubed, or let's go A1x cubed plus A2x squared plus A3x plus A4. Isn't that a third-degree polynomial? What does a 0 polynomial look like? The 0 vector. The coefficients must be?
They must all be 0.
You got it. All be 0. So it looks like this. The focus is on the 0 here. So there you go. That's what the third-degree 0 polynomial looks like. And of course, the answer as a real number is 0, right? But that's just what it looks like, the 0 in that vector space. Number 6 is the set of all 2 by 2 matrices, square matrices. So what do you think the 0 looks like for the 2 by 2? Again, you just have always 0. See, everything 0, 0, 0. So that's what the additive identity looks like. Okay, let me change back to the book. And there you go. So we're good on that one. So that was the additive identity. Now, next, it says, what is your additive inverse? So for instance, let's do, the additive inverse. Let's do, for instance, number 10. We'll do number 8 too, but just to do number 10 to get you in the right frame of thinking. The additive inverse, remember, the additive inverse of u is minus u. So what does the additive inverse for number 10 looks like? The set of all matrices that have 1 row, 4 columns. M1, 4. So let me switch to my notepad. And the set of 1 by 4 matrices. So the general form, we're out of 0, by the way. Now we think actually good numbers here. So let's say this is a scalar, first, second, third component, right? What is the additive inverse of this going to look like? The additive inverse is what you add to it to get the 0 vector, right? So the additive inverse is, what would it be for V1? What adds to V1 to make 0? Negative of V1, right? Additive inverse makes 0. You add and you get 0. What's additive inverse of V2? Negative V2. Of V3, negative V3. Of V4 would be negative V4. You see how that works? That's additive inverse. So if we have, let's say, in number 12. In number 12, we have M2, 2. You want to find the additive inverse of all square matrices of size 2, order 2. So this is what the matrix in general looks like, right? A 2 by 2 matrix. What does the additive inverse look like? What makes each of these 0, right? So what makes A 0?
Negative A.
You got it. Additive. So we add. So additive inverse of A is negative A, and likewise negative B, negative C, negative D. Now let's go back to number 8, because it's like, what is number 8? Number 8 looks like this. Now, what is this C negative infinity to infinity? This is C stands for continuous. So we're looking at the set of all continuous functions from negative infinity to infinity, right? The function, right? We want to find the additive inverse of, because that's, I just said based on what I read, C for continuous function. So I'm going to use the function notation. What do you think the additive inverse of f of x would be? Is, what do you add to f of x to create 0? F of x plus what is 0? It would be negative f of x, right? And there you have it. So that is the additive inverse of f of x. Again, this notation C, what does that, how do I know? C stands for all continuous functions. Call them f of x. There you have it.
So, Professor,
Yes, sir.
for It wouldn't be f of negative x.
No, it's because see, they have to add to 0 there. F of negative x, for example, now remember continuous functions. Let's say my f of x is x squared, right? And if I do f of negative x, what do I get?
To get the same function.
If I add them together, do I get 0?
No.
No. So that's why it's negative on the outside. So it's got to be negative f of x. Any function you make up, take opposite of it, you add it, you get 0. So that's why, thank you for asking that. So that's why, yeah, it's got to be a negative f of x. Okay, so we're good on that part. And again, thank you for asking, Angel. Anybody, please, if you have questions, ask. So now there you go. They got a whole bunch of these. Let's say for this one, determine whether the set together with the indicated operation is a vector space. I'm looking at 13 through 34 now. If it is not, identify at least one of the 10 vector space axioms that fails. Okay, so we are supposed to say again whether any one of these determine whether the set, each of these makes a set. And they give us an operation on that set. So based on the set and how they define the operation, do we have a vector space or not? If not, why not? So for instance, let's take a look at number 16. Let's take a look at number 16. Number 16, and I'm writing it down as I read it on my note on the paper. Number 16 is the set of all first degree polynomials. I'm sorry, number 16, the set of all fifth degree polynomials, right? Set of all fifth degree polynomials. Number 16, the set of all fifth degree polynomials with standard operations. And remember what standard operations are again, anyone? What do we mean by standard operations? Standard operations are addition. And what's the other one?
Multiplication.
Very good, scalar multiplication. Sorry, let me switch to my notepad. And there you go. So the set of all fifth degree polynomials with standard operation additions and scalar multiplication. All right. So what do you think? Is this set going to form a vector space? If not, what is wrong with it? Fifth degree polynomials. Is it closed under addition? Now, closed under addition means this. Will I add a fifth degree polynomial to another fifth degree polynomial and I always get a fifth degree polynomial? Is it true or false? You add a fifth degree polynomial to another fifth degree polynomial, and you always get a fifth degree polynomial. Is it true or false? So here is an example. Isn't that a fifth degree polynomial? I'm going to add it to another fifth degree polynomial. What is the result? X to the fourth minus x cubed, right? Is this a fifth degree polynomial?
No.
No, not a fifth degree polynomial. Therefore, we say this is not closed under addition. So the set is not closed under addition, because you're only looking at fifth degree polynomials. So yeah, the fourth degrees will not be there. Therefore, this is not a vector space. Not a vector space with standard operations. Let's take a look at another one. Let's look at number 20. Okay, in number 20, this time we have the set of all quadratic functions whose graphs pass through the origin with the standard operations. The set of all quadratic functions whose graphs pass through the origin. Well, let's take a look at these. So number 20, we're looking at all quadratic functions. Now the quadratic function is in the form ax squared bx plus c. Whose graph passes, I'm writing it, I'll show you my paper in a moment. Graph passes through the origin with standard operations. Okay, let's check this one out. Okay, now here the key is the way they've described this quadratic function. If the graph passes through the origin, so here's one, the graph passes through the origin, right? Here's another one, the graph passes through the origin. So how is this going to look like? The graph passes through the origin. This would work, wouldn't it? Am I on the right track here? Do these qualify the graphs? These pass through the origin, don't they? Now, whatever this quadratic is, what is f at 0?
0.
F at 0 here would be when x is 0, right? X is 0, you get 0, 0, and c must be 0, shouldn't it? You're right, f at 0 is 0 because it goes through the origin. Now, in the general form, this is f of x, ax squared plus bx plus c. When we go f at 0, that's a times 0, 0, b times 0, 0 plus c. So doesn't this, because it has to be 0, right, equals 0? Doesn't that mean c is 0? Therefore, all of these quadratic functions that pass through the origin are in this form. Therefore, the polynomial function is going to be in the form ax squared plus bx. This is the form we're looking at. Now, what do you think? Does that form a vector space? Let's see if we have closure. Remember, close under addition and scalar multiplication. Let's try closure, for example, where I'm trying to verify closure. What if I say f of x is x squared? Does that qualify as this form? That's in fact this one right here. The graph of x squared, doesn't it go through the origin? As long as c is 0, so any version of ax squared bx would do. B could be 0. And there you go. I have ax squared. This qualifies. A is 1. And just to be different, let me make my g of x be negative x squared plus x. See, now it's in the same form, ax squared plus bx. I don't have a constant. So if I add a constant, that's not going to go through 0. Now, Is this closed under addition? Do we have closure? That means f of x plus g of x has to look like this, right? If they look like that, then we say that the set is closed under addition. And what do I get when I add f of x and g of x?
Just x.
Only x. And what do you think? Is this quadratic function?
No.
No, it's a linear function, right? Therefore, not closed under addition. Therefore, there's no closure on this one either, right? True. So there is no closure. Therefore, the set is not a vector space. Not a vector space. Now, let's take a look at another exercise. We're going to go to another example here, another exercise. How about, let's take a look at number 26. In number 26, we're looking at the set of all 2 by 2 matrices of this form. This has to be the form. So let me write this one, number 26. We have the set of all 2 by 2 matrices in the form A, B, C, not D. Instead of D, that element, second row, second column is always 1. So what do you think? Is number 26 closed under addition? In other words, when I add 2 matrices, I will get a matrix that looks like ABC1. Let me help you here. I know this is a little abstract, so okay. Here's what I mean. I'm going to choose 2 matrices that are in this structure. Tell me if this is right or wrong. 3, 4, 5, 1. Is that matrix in the form that the exercise displayed?
Yeah.
Yes. What's important is the 1 here, folks. A, B, C, pick your own numbers. Now, I'm going to verify closure. Is it closed under addition? Now, you gave me, Angel, you're welcome to chime in. Give me another 2 by 2 matrix, any matrix you like. I'll pick this one for you. You have no choice on that element, right? That's always fixed. What would you like A, B, C, B?
2, 3, and 4.
Okay, let's add them. Now, at this point, we're doing addition of 2 matrices, right? This is the form of the matrix. The form of the matrix does not dictate the addition of the matrix. The addition rule of matrices, we know that from previous chapter, right? So what would be the sum of first element, first row, first column? 5. First row, second column, 7. Second row, first, 5 and 4 is 9. And second is 2. So what do you think? Is this matrix in the set? This one. Is it in this set? Look at this one, look at that one. Does it look the general structure? Does it look like this?
No.
No. See, the set says your second row, second column must be a 1. It's not. So if this was a vector space, you see that? There is no guarantee that the sum will exist this sum does not exist in this set. So the set fails to close. So it is not a vector space. This is not a vector space. And because it is not closed under addition, not closed under addition. Now, what about scalar multiplication, by the way? Let's say somebody says, you know what, I'm going to try scalar multiplication first. Let's do that. Because we haven't done that yet. Let's try scalar multiplication. Is it closed under scalar multiplication? So for example, can I say -1, 7, 10, 1? Is this a matrix in this set?
Yes.
Yes, because the key is this one. These numbers are anything you want. Let's do scalar multiplication. So let's do 5 times that. Now, scalar multiplication, forget the set. How do we multiply a number times a matrix? Do we not multiply every element by 5? So it's going to be -5, 35, 50, and 5. True? What do you think? Is the set closed under scalar multiplication?
Also no.
No. So not a vector space. It's not closed under addition, and then nor, and all it needs to fail is one or the other, but what we just showed is neither of them works. All it takes is one of them not working. So if somebody just did that, you're good. Nor scalar multiplication. And there you have that one. Isn't that cool? Okay, so this is how you work these. Let's see. It's getting kind of late. I don't want to keep you too long, but let's take a look. Everyone okay, by the way, on number 26? We're good on this one. Any questions, anybody? Again, I know you probably haven't done anything like this. It's a little abstract, but hopefully this exercise 26 kind of puts it in perspective, and everyone okay with this one. All right, so I'm gonna do this. I'm going to stop the recording here, and because we're almost done, folks.